Most induction motors are started directly online. But when large motors are started that way, due to large starting torque current surges, they cause a disturbance of voltage on the supply lines. The current at motor starting can be anywhere from 5 to 8 times the motor's full load current. Direct online method is only suitable for the motors up to 7.5 kilowatt motors. To limit the starting current or the starting torque current, induction motors are started using star-delta method. Star-delta is a reduced voltage starting method. Voltage reduction during star-delta starting is achieved by physically reconfiguring the motor windings as illustrated in the figures. The reconfiguration of the windings of the motor is achieved by 3 contactors and a timer. We will discuss the reconfiguration later in this video tutorial. If we start a star-delta starter, first motor will run in the star mode by turning on power and star contactors, and motor starts running with less starting torque current and slowly ramps to almost 60% of its RPM. Once the time is up, the star contactor turns off and delta contactor turns on. This will reconfigure the motor winding to delta configuration, and full voltage applies to the motor winding via power and delta contactor, and motor goes to its nominal speed. So the reason why we use star delta starting is to reduce the starting torque currents for the big motors under heavy loads. If we open a motor connection box, it will be looking like this. There will be 6 wires connected to the 6 terminals. These are the ends of the 3 coils of the motor windings connected to the terminals in this arrangement. So basically we have 3 coils of windings inside the motor, U, V and W, with inductance L1, L2 and L3 respectively. If we connect U1 end of the red coil with the W2 end of the blue coil and W1 end of the blue coil with the V2 end of the yellow coil and V1 end of the yellow coil with the U2 end of the red coil, connection will look like a triangle, and this is called as delta winding configuration. If we apply 440 volts 3-phase supply with each phase of 220 volts AC, the motor will start to run with fairly high starting torque current. Because as we apply the voltage supply to the motor winding, it will try to overcome the rotor inertia and try to gain the speed from 0 RPM to full motor rated RPMs. Thus, in the delta wiring configuration during motor startup, it tends to draw more starting currents, and in some cases can affect or lower the incoming voltage supply. If we look closely at the diagram, we can say that R and Y phase 440 volts is applied only across L1 coil, while Y and B phase 440 volts is applied only across L2 coil. B and R phase 440 volts is applied across L3 coil. You can say that 440 volt supply is applied to only one coil in all 3 cases. Now this is very important, just keep this noted. We will discuss this later in the star winding configuration. Now if we connect the 3 ends of the all 3 coils, it will look like this. This is a star configuration. If we apply the voltage across the end of the coils, the motor will start to run, but this time slowly gains speed and the starting current will be fairly less as compared to the delta winding configuration. If we look now closely at the diagram, we can say that R and Y phase 440 voltage is applied across L1 and L2 coils. Y and B phase 440 voltage is applied across L2 and L3 coils. B and R phase 440 voltage is applied across L3 and L1 coils. We can say that 440 volts supply is applied to the two coils in all three cases. That doubles the inductance of the motor coil. This means that in star connections, 440 volts is applied to the two coils in series with each other. That's why the motor starts to run slowly and draw less amperes as compared to the delta connections, where 440 is applied to only one coil and motor starts faster and draw more current. Now let's see how this switching from star winding configuration to delta configuration happens automatically using contactors and a timer. Star delta starter consists of power contactor and a thermal overload, delta contactor, star contactor and a timer. To switch on and off, we need a green and a red push buttons. The three-phase supply will be applied across the motor terminals via power and delta contactor. Star contactor is used here to convert the motor winding configuration to the star configuration by shorting the ends of the windings from one side. Control phase is applied via thermal overload NC contacts to turn on the power contactor and the timer. Normal close contact of the timer will turn on the star contactor. When the start time is up, the star contactor turns off and a delta contactor turns on via NO contact of the timer. Star and delta contactors are interlocked, means only one out of these two contactors turns on at once. If we press the green push button, it will turn on the power and the star contactor and the timer starts timing. The three-phase supply is applied to the motor via power contactor and motor winding is in the star configuration because the star contactor has just shorted the end of the winding coils from one side. This doubles the inductance of the motor coils and motor starts to gain speed slowly and draws less starting amperes. As the motor slowly ramps up and gains the 80% speed of its nominal RPM, the starting timer is up and it turns off the star contactor and turn on the delta contactor. This will change the motor winding configuration to the delta and three-phase power is applied to the free ends of the motor terminals via delta contactor. And now the motor will run with the full power and gains the nominal speed. So we can say that the star delta motor starter is used to start the motor smoothly with less starting torque current. It will save the power and make the life of the parts connected to the motor more longer. So that's today's video and this is how a star delta starter works. I hope you liked today's video. Please subscribe to my channel and until next video, take care and goodbye.